So just a recap here, we use the boundary condition here, okay, for the two types of electric fields. One is the electric field that is perpendicular to the plane of incidence, and the other one is the electric field that is parallel to the plane of incidence. So this is the electric field that is perpendicular to this plane of incidence. We have this at, come on, why is it not writing? What's that? Is it raining? Why it doesn't allow me to write? That's strange. Come on. Okay, so it doesn't allow me to write. So we use the boundary condition for magnetic field and electric field, and then we derived the coefficient called amplitude reflection coefficient, which is the ratio of amplitude of electric field reflected over amplitude of electric field incident. And we also got this ratio. Okay, so that's what we did last time, and then we did this problem by using this formula. And we did the same thing for the electric field that is parallel to the plane of incidence. Okay, here the electric field, this electric field is parallel to the plane of incidence. Plane of incidence is this plane, and we got the similar formula. These formulas are called Fresnel's equations. Okay, this R parallel is amplitude reflection coefficient, transmission coefficient, and these are for parallel electric field. And we also did the problem, and we saw the limiting cases, and then we derived an equation for a case or condition when this R parallel is 0, when there is no parallel reflected electric field. That particular angle of incidence is called Brewster angle or polarization angle. So we got the expression for that. So this gives us Brewster angle in terms of refractive index of the transmission medium and incident medium. And we also did the lab on this one. So if you haven't done lab, you can do that this week. Okay, so today, so we will talk about total internal reflection. Okay, so this would be our discussion for today. I still want to write on this, but I don't know why. Okay, now it's working. So using the Snell's law, we can write the critical angle in terms of refractive index. So this is the Snell's law. If you have two medias, one is with NT and the other one is NI, and the light is going from this medium NI to the NT, and in this case NI is greater than NT, meaning this medium is denser than this medium, okay, less dense. For example, this one could be glass and this one could be air. So when light goes from glass to air, light is refracted away from the normal, like that. Okay, so this is the Snell's law for this boundary. And in case of the critical angle is defined as the angle for which angle of refraction is 90 degrees. So let's see. So for angle of refraction to be 90 degrees. That is the angle of refraction. The angle on this part, this is called critical angle theta c. Okay. So now if you use that in this expression for Snell's law, angle of incidence, this would be 90 degrees, and this is, sorry, this one is incidence is critical angle, okay, and this would be 90 degrees. So using that, critical angle would be nt over ni. Okay, so that's the ratio. Now let's look at the expression we got in the previous lecture, this Fresnel's equation for R perpendicular. So this R is basically the ratio of reflected light over incident light, and this is for the perpendicular electric field, or electric field perpendicular to the plane, and this is the expression we got last time. Okay, so now let's use this expression for this R perpendicular. Okay, so we can write this as ni over nt. So if I divide this numerator and denominator by nt, so divide this by nt and this by nt, then I get this expression. Okay, so ni over nt, ni over nt, and for the second term you cancel nt and nt, you cancel nt and nt, so you get 1 and 1 there. Okay, so this is the same expression with a little bit of modification. Now we can write this cosine I in terms of sine I, because we want to use this expression in this one. So somehow I need to change this cosine into sine, and we know this formula for sine and cosine. So cosine theta is, cosine square theta is 1 minus sine square theta. So that means I can write cosine theta is equal to square root of 1 minus sine square theta. So that's what I can write, okay, like that. So cosine of theta transmitted angle is equal to 1 minus sine square theta of transmission angle, and I have this here for sine theta c. Okay, or let's do one more thing here before we use this one. So let's start with this one first. So sine theta, oops, too fast. Okay. So we have this for the Snell's law. So sine theta t is equal to ni nt sine theta I. So that's the Snell's law. Now we use that in this equation. So sine theta t is that. Okay. And now I want to write this expression, our R perpendicular, this expression in complex form. The reason I want to do that is to simplify our math. When we use complex number, there is a trick that you can use to deal with the ratio, this kind of ratio. I will show you that later. It would be much easier to handle this kind of ratio when we have complex number. Okay, we'll see that in a second. So that's why I want to write this expression in complex form. So for that, let's flip the sides. So move this in front and move this one to the back. When I do that, I will have, so minus common. So you take ni nt sine theta I minus 1, just that's squared. I'm just flipping the terms so that I can pull this minus out of the parentheses, and square root of minus is this complex number I. Okay, so this is just square root of negative sign, and everything else is same inside the square root. Now with this cosine t, I can write this expression, okay, in complex form. So I have this cosine t here and cosine t here. So replace those cosine t's by this one. So when I do that, we get this expression. So this is as it is, the first term, and the second term is that. Okay. Now we have our r perpendicular in complex form. Now you will see why we are doing this, because it will make our job a lot easier when I use complex form. So here we have this equation. I'm just rewriting this thing here. Okay. Now this is in this form. Okay. So this is z star. So if I consider this whole thing to be a complex number z, okay, this is z, then this bottom one is z star. Z star is complex conjugate. So if you have a complex number x plus iy, then complex conjugate of this complex number is x. You use minus sign for the one with this I. Okay, that's the complex conjugate. So this is the complex conjugate of this upper term. So this would be z star, and the magnitude of this z star is always 1. If you have the ratio of a complex number and its complex conjugate, the magnitude of that would be 1. You can show that very easily in this way. So this r is the magnitude of complex conjugate, which is so whenever you are finding a magnitude of a complex number, it's square root of z squared. Okay, and this usually we don't write z squared, z star. Okay, so if you have taken a quantum physics or quantum mechanics, we use this a lot in quantum mechanics. So any complex number has the magnitude given by square root of z star. So we can do the same thing here. So if I want to find the complex magnitude of this complex number, I need to take the square root is missing here, square root. Okay, so z star and the complex conjugate of that, this z star. So this thing is a complex number, and then the complex of or the conjugate of that, this gives us the magnitude. Okay, so I have that, and when you do the conjugate of this thing, you'll have star, g star, conjugate of z is z star, and conjugate of z star would be z, because if you take the conjugate of this, you get the same thing back. Okay, x plus iy. So we can cancel that and that, and that will give us 1. Okay, so that means whenever we have this kind of expression, the magnitude of that is given by 1. So the magnitude of this ratio is 1, but although the magnitude is 1, there is difference in the terms on the up and on the numerator and denominator of this expression. Okay, so when we know that r is E naught r over EOI, so the ratio of that, the magnitude of the ratio of that is 1. So that means EOR would be equal to EOI. Okay, magnitude wise that's true, but they still have difference in the phase. Okay, that's what you will see when the light is reflected. The incident light and the reflected light, they will have opposite phase. Okay, if you are using this kind of representation, if it is if this part is crest here, then that part will be trough on this part. Okay, it will just flip. The top becomes bottom and bottom becomes top. So there's 180 degrees phase shift. So we need to incorporate that in our expression. Although the magnitude is 1, so we still have this phase factor. This tells us that there is phase difference between these two things. Okay, so that means they only differ in the phase. So that means we know that EOR and EOI are same magnitude wise, but phase wise they have some phase difference, and we use this to represent that phase. So this represents the phase difference between EOR and EOI, meaning when the electric field is reflected, you will see there is 180 degrees phase shift. And this is true when the beam is totally reflected. We are talking about total internal reflection. Okay, so when our this angle of incidence is greater than critical angle, the ray would be reflected back in the same medium. It won't go up or to the surface. So this is TIR. And this thing is true for TIR. We are talking about total internal reflection. Okay, because we use the condition here. This is for total internal reflection, because we are finding this R perpendicular. So we saw that this R perpendicular has this form, okay, this ratio of complex with the complex conjugate, where our Z, this is that, okay, because that's what we have here, right? So this thing, we are considering this to be Z, and this thing is Z star, conjugate of that. So this R perpendicular is of the form of the ratio of complex number and its conjugate. So that means if we multiply the numerator and denominator by Z, it will make the denominator real. Okay, so let's say you have a complex number or ratio of two complex numbers, and you want to make this a real. Let me show you the real example here. So let's say we have x plus iy and x minus iy. If I want to make this denominator a real number, then what I do is multiply numerator and denominator by that, okay, the complex number on the top. So this will give us this on the just on the bottom. So x squared minus and minus plus, that would be minus y that squared. Okay, a minus b, a plus b, so a squared minus b squared, x squared plus y squared. So this is a real number. So if you want to get real number on the bottom, you just multiply this by z. Okay, so that's 1, so you can do that, and that will give us a real number. So let's do that here. So multiply both sides by z and z, that gives us z squared. So this z and z is z squared, okay, but star times z is magnitude. There is difference between these two. This is just the square of the complex number, but this gives us the magnitude, okay, magnitude squared. And this could be written as that, okay, magnitude times, because z is complex, it's like a vector, okay, this is a complex number is like a vector. So you have some magnitude times its phase. Okay, so that's that. So magnitude times its phase is the complex number, and you have square there. So that's z squared, square of that squared. We cancel that, and that will give us this thing. Okay. Now this shows that the phase angle for r perpendicular, this is the phase angle for r perpendicular, is twice the phase angle for z. Okay, so the phase angle we got here is the phase angle for z, this one. Okay, and we see that this is twice that phase angle. So we can write phi perpendicular is 2 times phi, okay, and that gives us 2 times phi. To find phi, it's basically tan phi is given by real imaginary part over real part. So basically what we are trying to do is, we have this imaginary number on this y axis. You have this z is some complex number x plus iy. If I want to represent this on this plane, let's say this is our z, our real part would be x. We can just call this real part, and this would be our imaginary part. Okay, that's y. And if I want to know this angle is given by tan inverse tan theta or tan phi. Let's say phi is equal to imaginary z, this part, over this part, this z, imaginary part of z, over imaginary part of a real part of z. Okay, so this over that, imaginary part over real part of z. So that's what we have here. So 2 times tan inverse, and then imaginary part, if you go back to our expression here, this thing is the real part, this thing is the imaginary part. Okay, so that means to find phi, we need to take the ratio of this imaginary part over the real part. Okay, so when we do that, we get this expression. So this is the imaginary part, that's the real part. And you can take this, no, this is fine. So you can take this up. So that's that, nt over ni, and that's everything else is same. Okay, so this is the phase angle. Here alpha is this thing. We are considering this to be alpha. Just simplifying. Okay, so that gives us the phase angle, phase shift, I mean, where alpha is given by that. And this is for the total internal reflection. This works only when incident angle, this theta I, is greater than theta c. Okay, so this is the phase shift in the reflected light. And we can do the same kind of treatment for r parallel. This is for r perpendicular. R parallel is defined as that. Okay, same kind of thing. We already got this last time. This is Fresnel's equation. The spelling is Fresnel, F-R-E-S-N-E-L, but it's pronounced Fresnel. Fresnel equation. And then write this in complex form. And just like we did last time, do the same thing. You get this expression for EOI and EOR, and then you get this phase angle, and then that gives you EOR in terms of EOI. Okay. So now let's talk a little bit about application of TIR. Okay. So you don't need to worry much about this one. We won't be using this for numerical problems. So this is again same thing, just rewriting. So here you see total internal reflection. So the light hits the prism, okay, and that's the perpendicular or normal. So instead of going out, because this angle is greater than critical angle, so it doesn't go out. Instead, it is reflected in the same medium. Okay. So that's the total internal reflection. If this angle is less than critical angle, if this is less than critical angle, you see it will go out. Part of it will be going out. There is some reflection, but there is also refraction. Okay, because this theta is less than critical angle. But when the theta I is greater than critical angle, so you won't see any light here. Everything would be reflected back. Okay. So here are some of the applications. So usually we use this principle to steer beam inside prism. So you want to change the direction of the light from this direction to down direction. You can use a prism, and you use the total internal reflection, so it will move it down. So in some cases, let's say you want to turn around the beam. Okay, so the beam is moving this way, and it will reflect internally, and again reflect internally. So there are two TIRs here. So one is at this interface, another at this interface, and it will go back in the same medium. Okay, so you can use this as a TIR, as beam steerers, which is what we use in binoculars. In binoculars, you see the light enters the tube. It is internally reflected here in the prism, and then it will move in. It will hit another prism here, and this prism also steers the beam, and then it moves up. Okay, basically, it helps to compress the path, so that the light doesn't have to travel long straight path. It will just travel longer paths internally, so you don't have to make long tube. Okay, so those are some other things. The other important application is in optic fiber. So nowadays we use this optic fiber for transmission of internet signals, right? Internet cable, as internet cable, because there is very small amount of signal loss in optical cables. Okay, in case of the wire cables, there is significant amount of signal loss, but in case of this one, it's very little loss, and it's very inexpensive, because usually these are made up of plastics or some kind of silica, so it's abundant, so it's easily available. Whereas the wires are more expensive, right? You have to make copper wires, and it's difficult to make. And then you can send wide band of signals in very narrow, thin wire, thin optical cable. Okay, you can have, like, see if I can show you a picture. You see here, I mean, each of these optical fiber carries millions of signals, and you can fit these in like a small like a tube. See, I mean, you can fit like hundreds of optical cables in a small a tube. So usually to protect the optical fiber, so you have this optical fiber in the middle, you use something called cladding. Okay, cladding protects the inner core, and cladding has refractive index less than the refractive index of the core, because that's what you need for total internal reflection. The necessary condition for total internal reflection is, you need to pass the light from denser medium to less dense medium. Okay, so this is the core. So core needs to be denser. So n I of or n of the core should be greater than n of the cladding. Cladding is outside. Let's call that NT. So only when Ni is greater than Nt, when the light goes from denser to the less dense medium, it gets totally reflected. Okay, there are two conditions for total internal reflection. One is this condition, this should be denser than that, and the second condition is this angle should be greater than critical angle. So in case of optical cable, there is only 10% loss in the signal over a kilometer of distance. Okay, when the wavelength is at 1550 1550 nanometers, there is significantly less loss of signal. Usually the signal is lost where there is maximum curvature, okay, around this side. When it's straight, more or less straight, there is very little less loss. Okay, we talked about this last time. Okay, so now let's talk a little bit more about this, and then we'll come back to this one in a second, because there's a little bit more about critical angle. Okay, so here we have the boundary condition. The boundary condition is the light, let's say electric field, okay, on this side should be equal to the electric field on that side. Okay, the electric field should be continuous at the boundary. So let's say this is the incident light, this is the reflected light, and this is the transmitted light. Then the boundary condition requires that electric field incident plus electric field reflected, which is the total electric field on this side, okay, on the bottom part, that should be equal to electric field on the top, okay, EOT. This is the continuity condition. Okay. Now we saw in the total internal reflection that nothing goes in this part, everything is reflected back. That means that doesn't satisfy boundary condition. We are in the total internal reflection, we are seeing this to be 0, and that cannot be true based on the boundary condition. You cannot have discontinuity in the electric field. If you have some electric field down here, you must have some electric field up here also, right, because of the continuity condition, because of the boundary condition. So that means our boundary condition requires that although the electric field or although the light is totally reflected, we still should have some electric field on the upper part of the boundary. Okay. So, that is what it says. The boundary condition demands we need to have non-zero field on both sides of the boundary. So, let us say that our electric field on this part is given by that. Okay, that is the electric field, because we cannot assume that that is 0. Boundary condition does not allow us to make that 0. So, there is a finite electric field transmitted. Now, this thing is the vector product, dot product. So, if you have A dot B, you can write this as AX B x plus AY BY, right, dot product of two vectors. The same thing we are doing here. Okay. You can write that in terms of components, because this K, this is KT xi hat plus KT yj hat, right. So, and we know this R is xi hat plus yj hat. When you take the dot product of these two, only I hat and I hat will survive. So, you will have KT x, which is that, and on this one only j hat and j hat will survive. I hat dot j hat would be 0, j hat dot I hat would be 0, because dot product of these would be 0. Only the dot product of the same unit vectors are non-zero. So, we have that for this, and this KTX is our x component of this KTX is this component, and KTY is this y component, KTY, it is a vector. So, that means this would be, if this is angle, if this is theta t, then this side would be KT cosine theta t, and this side, the side that is away from this angle, the side that is near the angle gets the cosine. That is something you learn in introductory physics, and the side, this side that is away from the angle, that would be KT sine theta. Okay. That is what we have here. So, x component has KT sine theta, which is this one again, and KTY is KT cosine theta, which is this one again. Okay. So, now let us go back to our the way we treated the previous one. So, we can write this cosine t. So, I want to write this in complex number form. So, to express this in complex number form, so write this cosine t in terms of sine t. So, two things I want to do here. One is I want to use Snell's law, and I also want to express this in complex form. Okay. So, for that, let us write this cosine theta t as that in terms of sine theta, because Snell's law has only sine. So, I need to convert this cosine to sine. That is what I am doing here. And now, once I have that, you switch the sides, bring this sign in front and one into the back. For when you do that, you will have minus inside the parenthesis, outside the parenthesis, and then minus of the square root will give us I, okay, complex number, and everything here is same. And then, so let me just show you one step here so that you can see what I am doing here. So, I just flipped it. So, minus sine square theta t minus 1. That's what I did. And then if I take this out, I get I here, and then this sine square theta, using the Snell's law, I can write this as ni n t sine theta I. Okay, just using the Snell's law. That's the Snell's law. And then minus 1, which is what we have here. Okay. So once we have that, now let's use this expression. So we have this expression. This one. So kty is kt cosine t. Okay, so kty is kt cosine t. We have kt, and cosine t is, we got cosine t to be that, okay, which is what we use here. I will take maybe a couple more minutes before we finish this, because I want to finish this. Okay, so that's the expression for kty, and ktx, we see here ktx is this one. So kt sine theta t. So kt sine theta t, you can use Snell's law for that. Using Snell's law, you get that. Okay, because nt sine theta t is equal to ni sine theta I. So use that, and then you replace sine theta I by that. Now you use these two expressions, this one and this one, in this expression, okay, for the electric field. So electric field is E naught t sine I k dot r. So k dot r, this is that, and then use these ones. Okay. So when you do that, you get this expression. It's a long expression. And what we did here is we are separating the one with I term. Okay, this one is with the I term, and this one is without the I term. So the one that has I term is kty, and the one that doesn't have I term is ktx. So in this expression, we have ktx term and kty term. The one that is kty, that will get this complex number term, and this one without complex number term. Okay, so we get that. This thing is basically telling us that the electric field would decay exponentially. Come on. See here, we have this exponential thing here, so that tells us that it decays exponentially. And this tells us that the electric field is oscillating. That means if we have this total internal reflection, it will transmit on this side, but it will decay very, very rapidly. Okay, that gives us how it decays. Okay, so it will decay in very short time, in very short distance. It will not go very far, so it will just dies off. And so you see here, so you will see this light incident on this part, and then some electric field will be present here, but it will decay exponentially, but most will be reflected. Okay, but if you bring another medium very, very close to this medium, okay, so you will see maybe the electric field up to a certain distance, up to here. So if you bring this pretty close to this prism, closer than the distance within which it decays, then this will just show up here. Okay, instead of decaying, now it will travel on this medium. So this kind of phenomena is called frustrated total internal reflection. Okay, so this part, this wave or this electric field that shows up on this side is called evanescent wave, okay, which is this one. Evanescent wave is the wave that you see on this side, which decays very, very fast. And if you bring another medium pretty close to the first prism, then the evanescent wave will travel through that, okay, without decaying. That's the frustrated total internal reflection. And this is analogous to quantum tunneling. You might have, I don't know if you have seen this in quantum mechanics. So you have this wave traveling through some medium. When it goes to the medium that has greater energy, greater potential, it will decay. Okay, it will decay, and when it sees the one that has less potential, it will again come out oscillating. So this is quantum tunneling. The same thing happens here. Okay. Now there are lots of application of this frustrated total internal reflection, like in the fingerprinting. Okay. So in the fingerprinting, the TIR, you see the TIR from the fingerprint valley. So these parts result in TIR, total internal reflection, and the ridge ones, these ones, okay, these parts result in frustrated total internal reflection. Okay. So I think I will stop here. Maybe we'll discuss this next time because we are out of time. We'll continue this next time.